The second example is, the IRS claims that the mean amount of time it takes to transfer tax information from a tax return to a computer record is 35 minutes. So we have our population mean, 35 minutes. Before they will invest into a new system, they decide to do a test run to determine if the new system is significantly better than the present system. So we have a present system that transfers tax information in a mean of 35 minutes. That's what the existing system can do. The new system, the claim is that it's significantly better than 35 minutes. Significantly better than the present system, so significantly better than 35 minutes. What does significantly better mean in terms of computer information? Well, transferring computer information or transferring tax information from a tax return into a computer, if it's 35 minutes now, a better system would do it in less than 35 minutes. So that's going to give you an indication of the direction of the test. 400 tax returns are randomly selected, and the data is transferred using the new system. So you have your sample mean, 400, and you're told that the mean amount of time it takes to transfer the data from a tax return to a computer record is 34.3 minutes with a standard deviation of 4.2 minutes. So as you're reading this, you should recognize that this is the mean for the sample of 400, and this is the standard deviation for that sample of 400. So we have X bar and we have S. Based upon this sample, should the IRS invest in the new system? Use an alpha of 1%. Okay, so you have the population mean. You have the words that indicate the direction, which means less than in this case. You have the sample size. You have the sample mean of 34.3. You have the sample standard deviation of 4.2. You have an alpha of 1%. You don't have the population standard deviation, so you're going to be using the t-distribution. The hypotheses are stated in the same way. We're going to state HO, the population mean amount of time it takes to transfer tax information from a tax return to a computer record is 35 minutes. So the null hypothesis is going to assume that the new system will be no better than the old system. The new system will produce population mean of 35 minutes as well. So that's the assumption, but we're trying to disprove that assumption. We're trying to prove that it's going to be less than 35 minutes. So that becomes our alternative hypothesis. Symbolically, our null hypothesis is mu equals 35. The alternative hypothesis is the one with direction. We're going to state same words that we have in the null hypothesis, except when we get to this point, instead of saying is 35, we're going to state is less than 35. So the population mean amount of time it takes to transfer tax information from a tax return to a computer record is less than 35 minutes. Mu less than 35. Our alternative, our null hypothesis states the status quo, basically that the new system is no better than the old system. The alternative hypothesis states that it's significantly less. Mu is less than 35. Ideally, we want to prove that it's so far to the left, so far that it's enough to reject the null hypothesis. So let's move forward and see what this test looks like. The mean of the sampling distribution and its correct symbol. Like the last example, we have a collection of sample means, and the mean of all sample means is mu sub x bar. Its value is the same as the mean of the population, which is 35. Okay, so mu sub x bar equals 35. Normal or t, it's the t distribution because sigma is not known. Again, so you don't have the population standard deviation. You can either state population standard deviation is not known or sigma is not known, whatever you prefer. So you should note that you're going to use t-test on your calculator when the time comes to use the calculator. Your decision rule, first take a look at a picture that you should produce. You start in the center of a bell curve with mu sub x bar equals 35. The mean of the population is 35. Because this is a less than test, your test is on the left, and so you're going to shade in an alpha of 1% of area in the left tail. Any p-value that's smaller than alpha is going to be enough evidence to reject the null hypothesis. If a p-value is larger than alpha, which means the x-bar falls somewhere over here, or anywhere from here to here, anywhere in the white unshaded area, that's going to cause us to fail to reject the null hypothesis. It means that our sample evidence isn't strong enough and we cannot reject that the new system is any better than the old system. The new system has a mean of 35 as well. So our decision rule, reject HO at alpha equal 1% if the p-value of the sample statistic is less than or equal to 0.01. We always want the p-value to be smaller than alpha. A p-value that's smaller than alpha indicates that x-bar is far away from center. That's what we want, as far away from this center as we can get. So we're going to compare p with, or the p-value with 0.01. The sample statistic has the symbol x bar and its value from the problem is 34.3. And now you're going to go to your calculator with this information. Let's see, what do we start with? The standard deviation is 4.2. So on our calculator, when we run t-test, stat tests, number 2, t-test, okay, you're going to put your mean of 35, x-bar 34.3. Just an aside here. If you were just looking at these numbers and you saw that the new system produced a sample mean 34.3, would you think that it's significantly less than 35? It doesn't appear to me to be significantly less than 35. I would say that that new system really isn't so much better. But again, I'm not looking at the p-value. When we look at the p-value, we're going to see how much better it actually is. So let's see. Sx is 4.2. Sample size is 400. And the direction of our test, the direction of our test is on the left, so we're going to use the less than symbol and calculate. So we have a p-value. Now take note that there's scientific notation at the end of that value on the calculator. 4.6915014 e negative 4, which means times 10 to the negative 4th. So we have to take this number and convert it into standard notation. So we have to move our decimal point from this location 4 places to the left. So when we do that, we're going to see that we have a p-value that is pretty small. Smaller even than the last example. So if you think 4.69 and then you have to move your decimal places 4 units to the left, you end up with 0.000469, and when rounded to 4 places is 0.0005. This is a very small p-value, a highly significant p-value, which means, let's look at the picture, what that means now. Alpha of 1% is much larger than the p-value 0.0005. 0.01 is larger than 0.0005. This p-value puts x bar much farther away from center than we would expect. I mean, 34.3, you wouldn't think it was so much better than 35, but given the mathematics of this now, we really see that it's very far off. It's very far off to the left. Okay, so the p-value, which is in orange, is smaller and fits inside alpha, and so we say that 34.3 is very significant. Its value is less than 1%, so it's a very significant p-value. And so when p-value is less than alpha, we reject the null hypothesis and accept the alternative. So in this case, we reject HO and accept HA at alpha equal 1%, just like the last example. And the question, based on the sample results, should the IRS invest in the new system? And you should say yes, the IRS should invest in the new system. So that alone is sufficient. If you need an explanation for your own understanding, here's why. When you reject the null hypothesis, you reject that the population parameter is 35 when using the new system. So HO stated that the new system was no better than the old system. The new system produces a population mean of 35 minutes, just like the old system. But our hypothesis test showed that the mean is significantly smaller than 35. Since the IRS is interested in decreasing the processing time, it should invest in the new system. Okay, so based on the wording of the question, you really have some thinking to do sometimes, because the question can really throw students. You can get a hypothesis test entirely correct, but then when it comes time to answer the final question, you could get it wrong if you don't understand what you're rejecting or what you're failing to reject. So always go back to the words of your alternative and null hypothesis to help you figure out the answer to this question. Now we look at the possible error, which are type 1 or type 2 errors. We're going to begin with a chart, and I always recommend you recreate a chart just like this to answer these types of questions. Over here in these two boxes we have the actual state, and in these two boxes we're going to put the decision. The actual state could either be that HO is true, meaning that the mean really is 35 minutes, or it could be that HO is false, which means that the mean is really greater than 35 minutes. So those are our two possibilities for what's truly correct, what's actual in this example. The decision that could come out of a hypothesis test is either that we're going to reject the null hypothesis, which means reject that mu is 35, or we're going to fail to reject the null hypothesis, failing to reject that mu is 35. Producing this chart for hypothesis test is going to always put the null hypothesis here and the alternative hypothesis here. And you're always going to have reject the null hypothesis here, rejecting what you stated in the null hypothesis, and failing to reject the null hypothesis here, failing to reject what you stated in the null hypothesis. When the null hypothesis is true, and you fail to reject it, which means you have not rejected it, you've made the right decision. If the null hypothesis is false, it's wrong, but you rejected it, you've made the right decision. Okay, so the null hypothesis is wrong, and you've rejected it, you've made the right decision. The errors occur when the null hypothesis is true and you've rejected it. That's called a type 1 error when you're rejecting a true null hypothesis. And the other error that you'll get is a type 2 error. That occurs when HO is false and your conclusion was to fail to reject the null hypothesis. So meaning that the mu is really greater than 35, but you failed to reject that mu was 35. So in this problem, we take a look at what our decision came out to be. What was our conclusion? Was it to reject HO or was it fail to reject HO? Well, in this problem, the conclusion came out to be to reject HO. So the type of error that's possible is a type 1 error. Type 1 error is possible when your decision is to reject the null hypothesis. A type 2 error is possible when your decision is fail to reject a null hypothesis. So in this problem, we might have made a type 1 error. Okay, we could have made a type 1 error, or we could have made the right decision. If the null hypothesis is really false, meaning that the population mean using the new system is greater than 35, and we rejected the null hypothesis that it is 35, we are right on track. We made the right decision. But there's a possibility, a small possibility, very small, 0.0005% chance that we made the wrong decision. It means that 400 tax returns were randomly selected, and we happened to choose, let's go back. It means that we chose, and there's a chance that our sample does fall on the far left of that bell curve, and the far left of that bell curve has a probability of happening is 0.0005. There's a chance that we incorrectly rejected the null hypothesis. Now, if we do that, if we incorrectly reject the null hypothesis, we make a type 1 error. And that's what we could have made in this example. So it means that the mean time of the new system really is 35 minutes, but we've incorrectly rejected this mean and made a type 1 error. So when you make a type 1 error, you falsely reject a true null hypothesis or incorrectly reject a true null hypothesis, which means that the population mean really was 35 minutes using that new system, but you've incorrectly rejected it. Okay, so when you reject the null hypothesis, a possible error is a type 1 error. When you fail to reject a null hypothesis, a possible error is a type 2 error. So let's take a look at an example where that may happen.